Sorry, yeah. Starting with a status on the Silicon Photonics platforms, and then new trends and requirements due to the next generation of transceivers, and then a conclusion. So there is a kind of landscape of what is available today in the field of high-speed transceivers. We have several big players like Intel and Cisco sharing the market in terms of intra-data center transceivers, but also other companies targeting inter-data center. Intel is particular because they are in-house fabrication. Most of the other players are relying on commercial foundries like Global Foundries or TSMC. And we have also startups like IR Labs and Wohlfeil Photonics targeting next generation integration of transceivers in a co-packaging approach. That means very close to the host chip, providing a high density and high bandwidth optical interconnects directly at the chip level. Let's have a look on the components of the devices needed to build the photonic integrated circuits that will be used in a transceiver. So we'll have a transmitter and a receiver chip, each of one integrating several passive and active building blocks, namely modulators, photodiodes, and passive functions like multiplexers, waveguides, and fiber couplers. To achieve this kind of circuits, you can rely on existing platforms in foundries, but also on pilot lines or R&D organization such as CEA-Leti or IMEC, proposing some MPW service. And what's the kind of process flow that is used to achieve this photonic integrated circuits? You can see here a cross-section of typical PIC circuits relying on SOI wafer. You can see the silicon, let me put a pointer. Okay, you can see here the SOI layer that is patterned to form the waveguides, and also with implantation of boron and phosphorus to form junctions that will be used as high-speed modulating section in modulators. And germanium epi used to form high-speed photodiodes. On top of that, we can build a back-end of line, starting with a heater that is used to perform some thermal control and thermal tuning, especially for modulators, and then typically a two-layer back-end of line. So we have a full set of building blocks and devices. Passive devices include routing features, wavelengths management like multiplexer, demultiplexers, polarization management, for example, polarization splitters for coherent applications, fiber coupling structures like grating coupler. You can see here 1D or 2D grating coupler, and DC phase shifters. All these components are part of existing design kits that are constantly updated, and including some parameterized cells for designers and models for simulations. Regarding active devices, the main building blocks are modulators and photodiodes. In our standard design kit, we can offer these modulators based on Mach-Zehnder structures with high-speed modulation section based on the PN junction, and using this architecture that has been optimized during the recent years, we can achieve 64 gigabit per second NRZ modulation or 32 gigabaud PAM4, and we are working on the next generation at 50 gigabaud PAM4. From the photodiode side, we developed some germanium silicon photodiodes with the same kind of performance in terms of bandwidth detection. You can see here an eye diagram at the output of such a device at 64 gigabit per second NRZ. So now, what are the new trends for transceiver development? First, as you have heard in the previous presentation, we have this increasing demand in terms of data rate. So we have to increase the modulation performance for each channel and combine several channels thanks to WDM or coherent architectures. We have also a new challenge in terms of density increase to target a terabit per second per square millimeter in order to be able to co-package our transceiver together with a host chip in the same package. And then we have also an increase of the complexity degree of the circuits. For example, for current applications, that means larger circuits, increased number of IOs, and also the need for EDA technology to help designers to automate the routing of such circuits. Finally, we have also this challenge of laser source integration. To cope with all these four challenges, we developed some add-ons to our core process, namely 3D photonics, relying on a nitride silicon layer integration in the flow, Threefive integration to form laser if you want to directly integrate lasers monolithically, or 3D packaging, that means leveraging existing technologies from the CMOS semiconductor world to Silicon Photonics in order to increase interconnection density. So let's review these three axes. First of all, silicon nitride add-on. So we rely on this additional layer with a very low thermo-optic coefficient. That is a very important enabler for WDM solutions because we need some thermal stability of the multiplexer, and also we need broadband extended coupling because traditional grating couplers are limited in terms of optical bandwidth. So let's have a look on the different building blocks we developed within the COSMIC project to achieve this. First, hybrid grating couplers relying on the dual layers of nitride, silicon, and nitride to obtain increased optical broadbands of the grating couplers, that is a structure that is used to couple light into the optical fiber. An alternative is to use edge couplers. In this version, in this structure, we have to increase the beam size of the beam from the circuit to allow some efficient coupling to a lens fiber. And here also we can introduce this nitride silicon taper to enhance this capability of optical coupling. Finally, CWDM multiplexer have been designed to have access to some optimized multiplexer for CWDM transmissions. And these A-shell grating are made of silicon nitride layers. Second axis is to reduce the losses in the silicon waveguide, so in the core process. For this, we have to reduce the roughness of the waveguide. So starting from a preliminary study from CNRS in France within the IRT NanoElect project, we observed that applying an H2 annealing process onto the waveguides allow a dramatic reduction of the optical losses. So the challenge was to implement this new process in the full stack, so including the implantation steps and the back-end fabrication. So for this, we optimized the process, and we used a specific hard mask to keep the right shape of the waveguide. And so we observed state-of-the-art propagation losses down to 0.1 dB per centimeter for this 200 millimeter fabrication line. That make it competitive compared to 300 millimeter platforms using advanced immersion lithography. So you can see here the difference between the annealing and the non-annealing process with improvement in terms of propagation loss. We have assessed that there is no modification of the performances for the other passive building blocks, such as the grating couplers, and also a component that may be sensitive to difference in terms of shape, that is the directional coupler. So smoothing and no smoothing exhibit the same behavior. Also, we applied this process to the actives, and we recorded the efficiency of the modulator that is not affected by this process. And also, as the loss is reduced, we can reduce the total budget of a transmitter by several dBs, typically in a complete circuit. Finally, regarding the Threefive integration to form laser, so Kobe already presented the solution that has been developed, that is being developed within MASSTART, but in another project, we follow the same approach as Intel by developing a Threefive direct bonding onto SOI wafers. So here is the standard stack, and here is a stack with additional Threefive dies that are bonding using oxide-oxide bonding in the flow, and then we are able to build a new backend despite the specific topology. So to achieve this, we focus on two specific aspects of this integration. First, automated die bonding through the development of specific equipment and process. So now we are able to process some multi-die bonding, so dies from several types in terms of shapes, with die spacing of 400 micrometers, and it is scalable to 300 millimeter wafers. Another topic that needed to be addressed is access to a CMOS compatible backend of lines. Typically, Threefive contacts are made of gold that are prohibited in CMOS foundries. So we did a screening of different materials, and we identified some acceptable materials like titanium to build a new backend with efficient contact at the Threefive. So now we are able to build a two-layer backend of line relying on this new approach with state-of-the-art performances in terms of series resistance, and we applied it on a series of Fabry-Perot lasers recently. Now, if we want to build these Threefive materials in a stack containing nitride silicon, we have a problem because it's not mechanically compatible. So we develop a specific approach by using wafer bonding. From the SOI wafer with the patterning of the silicon and the nitride silicon layers, then we stick a carrier silicon substrate, and we remove the initial bulk substrate here to obtain an access to the backside of the SOI. And then by applying an amorphous silicon deposition and then Threefive direct bonding following our technique, we are able to add a Threefive integration capability to a process already equipped with the nitride silicon layers. That is one of the goals of our spin-off, Silicon Photonics. Some demonstration has been presented recently at SSDM. I won't comment it in details, but just to say that we have some achievements with DFB lasers demonstrated. Now to finish, the last but not the least is introduction of TSV structures inside our flow. That's because the interconnect density is increasing a lot. Here we have the story of the various transmitters and transceivers we developed within European projects at Leti since 2010, and starting from 10 gigs with wire bonding approach, now achieving 400 gigabit per second within the Cosmic project. So what is important to have in mind is that we started from standard wire bonding packaging technologies, then applying some flip chip of the control electronics, namely the drivers and the TIA, to the photonic chips. And then in this case, we still use wire bonding to connect the optical engine to the PCB. And now with the increase in terms of interconnects, we will improve this approach by applying TSV within the Silicon Photonics process flow. That is one target of the MASSTART project. So in the MASSTART project, this task will be held by Fraunhofer IZM. Anyway, in Leti, we also have some technical programs targeting this integration. So using either TSV last, that means the TSV is processed at the end of the back-end of line process, and with this kind of features of 200 micrometers thickness of the substrate during the process. And in parallel, we are also developing TSV mid. So in this case, it's a front-side etching that is perfect for the back-end of line process and requiring thinner wafers. A study is ongoing to study the stress and strain from the TSV to the photonics layers, and it will be presented soon. It has been presented during ESTC. So as a conclusion, we can see that silicon photonics transmitters still need some enhancements from the silicon photonics process. We have to increase data rates, density, and complexity. And so for this, we have to introduce new add-ons in the core process. These add-ons are silicon nitride add-on to enable access to WDM compatible devices. For the increase of density, and in order to fit with the co-packaging roadmap, 3D packaging and introduction of TSV is a must. And also for increased complexity, we have to require loss of waveguides, and so for this we develop a specific process at the state of the art using annealing. So all these challenges plus the laser integration are addressed at CEA-Leti. At this stage they are available in 200 millimeter wafer diameter, and then next year, we will move all these 300 millimeter platform.